Welcome to this lecture in which you will learn about the enthalpy of humid air, which is needed to make estimations of the energy usage of different processes. In this lecture, you will also learn how to estimate the energy needed to heat and cool air. What is enthalpy? Well, enthalpy is expressed in kilojoule or kilowatt-hour and is the total energy content of a system expressed with regards to a reference point at 0 degrees Celsius. For most substances, H varies almost linearly with the temperature as long as pressure or volume are constant. See here the enthalpy of dry air in blue as function of the temperature. By definition, for a thermal system, the enthalpy at temperature T minus the enthalpy at 0 degrees Celsius is C, the specific heat, times the temperature. Please note that C has the same value either in kilojoule per kilogram Kelvin or per degree Celsius. At 0 degree, by definition, the enthalpy of air is 0, so HT equals CT. If we want to calculate the energy needed, Q, to bring a mass m of dry air from T1 to T2, we can easily derive Q from the enthalpy. Q is the enthalpy at temperature T2 minus the enthalpy at temperature T1, which is therefore C times T2 minus T1, an equation that we know very well from other courses. Let's take the example of a mass MdA of dry air. The specific heat of dry air is 1 kilojoule per kilogram Kelvin. So Q is MdA times 1 times the temperature difference. Air is a gas containing dry air and water vapor. What about the enthalpy of water vapor? Well, it is the same story. So we have H minus HO equals C times T, where C is 1.86 kilojoule per kilogram Kelvin. However, air is always gaseous at our temperatures and pressures, but to get water vapor, we need to vaporize water. The latent heat of evaporation of water at 0 degree is not 0, but 2501 kilojoule per kilogram. That's the quantity of heat needed to evaporate 1 kilogram of water. So, instead of starting from 0, we need to start from 2501, which changes the scale on the left. This enthalpy of vaporization disappears when we look at the quantity of heat needed to heat water vapor from T2 to T1. Plus 2501 minus 2501 is 0. So here too we find a well-known equation. Now that we know both enthalpies of dry air and water vapor, we can easily calculate the enthalpy of humid air. If the mass of water is mW and the mass of dry air is mdA, then the enthalpy of the humid air is mdA times the enthalpy of dry air plus mW times the enthalpy of water. We remember from other lectures that if we look at 1 kilogram of dry air, mdA is 1 and mW is x, the absolute humidity in kilogram per kilogram dry air. We can therefore rewrite the equation as H is HAD plus x times HW. Using the equation from the previous slides, we come to H is the temperature plus x times 1.86 T plus 2501. Let's take a few examples. If I take a temperature of 0 degree, the equation is transformed to H is 2501 capital X, which is 2.5 small x in gram per kilogram. This is just a line in an HX diagram, this one. If we now take a temperature of 20 degrees Celsius, the equation is transformed to 20 plus 2.54x, which is this line. and the same happens for 30 degrees. In the Mollier diagram, the lines of constant enthalpy are plotted against the temperature and X. They are called isenthalpic lines. To give an example, if you want to know how the isenthalpic line H is 35 looks like, you can calculate it using the equation we have just studied. It leads to T is H minus 2501 times X divided by 1 plus 1.86 times X. So, for H is 35, the line in a TX diagram is as shown in the figure. Let's look now on an example how to use the diagram for the heating of air. Let's take a point at 10 degrees Celsius and relative humidity 60%. How much energy is needed to heat this humid air to 22 degrees? And what is its final state? At the starting point, the absolute humidity of air is 5 grams per kilogram. Mass cannot spontaneously appear or disappear, so this quantity of water vapor remains the same, meaning that the heating process must take place along the line of constant absolute humidity. So the final point with temperature 22 degrees must be here. The relative humidity has decreased to 30%, so the air will feel much less humid than when it was cold. And what about the energy? Well, at the final state, the enthalpy is approximately 35 kJ per kilogram. At the initial state, it was 23 kJ per kilogram. So the heat needed is 35 minus 23 is 12 kJ per kilogram. If we use the equation from previous slide, we have for point 2, H2 is 22 plus 0.005 times 1.86 times 22 plus 2501, which amounts to 34.7 kJ. For H1, we get 22.6 kJ, so the heat needed is 12.1 kJ per kilogram. Of course, reading it on the diagram is a bit less precise, but it is good enough. I have a question for you now. Would we obtain another result if we would consider the air as being dry air with zero absolute humidity? Well, on the diagram, we can see that the result would be identical. If we calculate it using x equals 0, we find Q is H2 minus H1, which is 22 minus 10 equals 12 kJ per kilogram. And we see that this is exactly equal to the equation we normally use for air. Q is mCp delta T, where C is the heat capacity of dry air, 1 kJ per kilogram Kelvin. So, in the end, we don't need this complicated diagram to calculate simple heating or cooling. This is because of the very small quantity of water vapor contained in air, generally less than 20 grams per kilogram. The sensible heat factor expresses the ratio of the enthalpy of dry air and the total enthalpy. It is a redundant factor as it can be deduced easily from the enthalpy of dry air at a certain temperature and the total enthalpy. So, by definition, the sensible heat factor SHF is HDA divided by H. Let's take an example of air at 20 degrees and absolute humidity 5 grams per kilogram. The enthalpy is then 32.7. You can calculate it like on the left or look at it on the diagram. To estimate SHF factor from the Mollier diagram, you just need to draw a line between dry air at 0 degree and the point for which you want to know this SHF, and continue this line up to the axis with sensible heat factor SHF, where you can read the value of 0.61, we will not use this factor further. If we look at the process in the psychrometric card, we see that heating at constant absolute humidity goes to the right, and the enthalpies can be read here. So, you see some small differences in the absolute values when compared to the Mollier diagram, but this has to do with the precision of the graphics and the goodness of your eyes. The enthalpy difference is identical. If you want to estimate the sensible heat factor SHF on this card, let's take again the example of air at 20 degrees and 5 gram per gram humidity. Here too, you need to draw a line between 0 and a point. You have then to draw a line parallel to this one, but starting in the middle of the small diagram above. Where this line crosses the circle, you can read the SHF 0.6 in our case. In another lecture, we already studied the cooling and dehumidification processes. Let's look now at the corresponding enthalpies. Let's start from air at 24 degrees Celsius and a relative humidity of 50%. Its absolute humidity is therefore 9.5 gram per kilogram, and when cooled, the process takes place on a vertical line as long as we don't cool below the saturation line. In the present case, where the air is cooled down to 13 degrees, the quantity of heat needed will be H2 minus H1 equals 48 minus 37 is 11 kilojoule per kilogram, which can also be obtained by using the equation Q is CdA delta T equals 1 times 24 minus 13 is 11 kilojoule per kilogram dry air. But what happens if we cool further? You may remember that further cooling takes place along the saturation line, where the water vapor condenses. The condensed water droplets have to be drained out, and as they have been leaving the air becomes drier. In the present case, the air was cooled down from 13 to 3 degrees Celsius, delivering air with an absolute humidity of 5 gram per kilogram. We can read on the diagram how much heat was needed for this cooling from 13 to 3 degrees. That is 37 minus 16 is 21 kilojoule. If we would make the calculations considering dry air, we would find 10 kilojoule per kilogram, which is completely wrong. When the absolute humidity changes, we need to consider also the enthalpy change of the water vapor, even if the absolute quantity is small. Let's consider the full equation for the enthalpy. We can derive easily that H2 equals 37 kilojoule, while H1 is 15.5 kilojoule per kilogram. The needed heat is therefore the difference, which is a bit more than 21, very similar to what we found in the diagram. So, when the absolute humidity changes, we cannot neglect anymore the energy content of the water vapor, and this comes mainly from its high latent heat of evaporation, 2501 kilojoule per kilogram. This brings us to the end of this lecture, in which you have learned how to calculate the enthalpy of humid air and how to read its value on Mollier and psychrometric cards. You also know now that the quantity of heat needed to heat or cool humid air can very well be calculated, assuming it is dry air, as long as the absolute humidity remains constant. If the absolute humidity is not constant, you need to consider humid air properties. Thank you. And you also studied the basic heating and cooling processes. I hope you have enjoyed this lecture. Thank you for your attention. Goodbye.